Okay, as we wrap up this chapter, I really quickly want to go over some synthesis strategies because there were a fair number of reactions we've covered. The first are a set of alpha functionalization reactions. So let's make a list. I like doing this at the end of chapters so that I have some sort of study guide to go off of when I'm taking an exam or a quiz. So let's start off with halogenation at the alpha position. And as you recall, we can do this on ketones or aldehydes as long as we have an alpha carbon with protons. So in this example, I've got my alpha proton here. Works with either ketones or aldehydes equally well. And we need to react it with our enolate or enol. And we can do this using two different techniques. We can either do our acid catalyzed formation of our enol, or we can use sodium hydroxide. Either of these will give you the enol intermediate. So let's make a note. And then, in the same reaction, we want to add elemental bromine. And then the enol that we created in the first step will react with the bromine to give our final product. Now the unique thing with this is, even though I'm calling them steps, really, you can do this as a one-pot reaction, meaning you don't need to have a step 1 and step 2. That's completely unnecessary. So this works quite well to get a halogen installed at that beta position, or sorry, alpha position. One important thing to note is with methyl ketones, you can actually do the haloform reaction. So with methyl ketones, you can convert to a carboxylic acid via the haloform reaction. That was the one that we did in our lab video. It's where you halogenate that alpha position 3 times. And then your hydroxide will actually kick off that methyl group that's now been halogenated as a leaving group, giving you a carboxylic acid that later you quench with HCl. All right, so this works well for aldehydes and ketones. We also saw something similar with carboxylic acids. Again, these carboxylic acids have to have alpha positions, and we can get a halogen to install at that alpha position, specifically a bromine, but we need to use a different set of reagents. We can't just use sodium hydroxide, or else that'll just deprotonate the carboxylic acid. So instead, it's a 2-step reaction. We use phosphorus tribromide and elemental bromine, and then to rip off the bromine that would replace this OH group, we would just need to quench with water or acid in our 3rd step. And that would give us our desired product. So these work really well for standard carbonyl compounds. Now let's take a look at alkylation rather than halogenation. And alkylation just means that we're going to be installing some sort of hydrocarbon at that alpha position. And we actually saw a variety of these reactions during the chapter. And I'm just going to give one that we actually saw. In this example, we have 2 different alpha carbons. We've got one on the right that's more substituted, and one on the left that's less substituted. We can actually control which position we react at. So if we want to get an alkyl group, like a methyl or ethyl, off of that more substituted carbon, we'd want to use a small unhindered base, like sodium hydride, and we'd want to run it at moderate to high temperatures. And then in the end, we need to make sure that this R group is relatively unhindered because it's going to be an SN2 reaction. So it works best if this R group is a methyl or primary group. If we want to get our alkylation to occur on the less hindered side, that's when we need to use a really big bulky base. So something like lithium diisopropyl amide at -78 degrees will give us this kinetic enolate. And then again, we can react this with an alkyl halide to give us the alkylation on the other side of that ketone. All right, so these work pretty well. We also saw kind of offshoot reactions of this, where we could make alpha alkylated carboxylic acids and ketones. So let's take a look at the first one. First one, we had diethyl malonate, and our goal, if you recall, is to make an alpha alkylated carboxylic acid. So this alpha position right here is the same alpha position that we had over here. This whole half of the molecule was lost as CO2. So that's getting blown off during the key decarboxylation step. And if you recall, we hydrolyze off this ester and make it into a carboxylic acid. So there's actually two important steps for this. So the first thing we need to do is form our enolate. And we use that alkoxide base that matches our ester. And then just like above, we can do an SN2 reaction with an alkyl halide. Again, this can't be too hindered because it's SN2. And then step 3, we treat with acid. That's the reagent that will hydrolyze this ester to the carboxylic acid. And then we use heat to blow off that carbon dioxide. So those are really important steps. We saw a similar reaction using a slightly different reagent. This is Ethyl Acetoacetate. Same thing. We can treat this with ethoxide, step 1. And then step 2, we can treat this with an unhindered alkyl halide. And then step 3, we can treat it with acid and heat. And just like above, the acid is going to rip off this ester and hydrolyze it to a carboxylic acid. And then the heat is going to take this whole group and we're going to lose it as CO2. So this alpha position is going to remain intact, and our R group is going to be installed off of that alpha site, but we're going to blow off CO2 in the process. So it is important to remember the mechanism for these. It could show up on one of our exams, so if you are ever stuck, make sure that you spend time to draw out the full mechanism. And then the key features students tend to struggle with, in my experience, is actually converting the ethyl ester to the carboxylic acid and then decarboxylating and losing CO2. So make sure that you do review that. All right, the last little bit is beta functionalization. So all of the above reactions, we were really tinkering with the alpha position on some sort of carbonyl compound. Well, if we have an alpha-beta unsaturated carbonyl, so in this case we got a beta position here and alpha there, we can actually react at this beta position rather than the alpha position. And this works well if it's a conjugated molecule, right? So we have to have that double bond there. And in order to do that, what we need is some sort of Michael donor in step 1. And so an example of a Michael donor could be something like a lithium dialkyl cuprate, but any Michael donor will work. So for example, it could be an enamine, or it could be a highly resonant stabilized enolate. It could be any one of those. This is just an example I'm choosing to use for simplicity. And then in step 2, we can treat this with water. And then by reacting this, we're actually able to install a new group off of the beta position of our alpha-beta unsaturated ketone. All right, the other reaction we saw, although it was earlier in the chapter, was when we take some sort of aldehyde, or in some cases ketones, treat it with sodium hydroxide and water under cold temperature conditions, we can get that Aldol addition reaction. And with the Aldol reaction, we're actually going to make a beta functionalized aldehyde. In this case, we've got an alcohol coming off a beta position. The alpha position is still that original alpha position, but if you remember, it actually attacks itself. And then, if we treat this with high temperature and more base, we can get an elimination type reaction to occur where we kick off hydroxide and we form an alpha beta unsaturated bond, meaning a double bond. All right, and then the last reaction that was key in this chapter was a similar reaction to the aldol, but instead of using an aldehyde or ketone, we use an ester. And we use a base to form our enolate, and then the ester will attack itself, and then we quench it with water, and by doing this, we can make a 1,3-dicarbonyl compound. So in this case, rather than a hydroxy group coming off the beta position, we actually have a CO double bond. And that's a classic sign that we're going to do a Claisen condensation. So make sure when you go through the book problems that you spend time to draw out the mechanism for all of these. I know it seems really complicated and a lot to remember, but my trick when I was doing this class was if I was stuck, I trusted my gut and I tried to do the mechanism as far as I could without checking my notes. That's one of the best ways to study. If you are looking for study guides, I've got a summary of reactions just pulled from the end of the book. This is useful when studying. And then I also have a fill-in-the-blank study guide where you can kind of practice, see if you remember all of the reagents, and fill those in on your own. All right, good luck studying, and let me know if you have any questions.